Hi everyone and welcome to the new DIA developer tutorial. My name is Samuel, I'm CTO at DIA, and I would like to welcome you to today's video where we are exploring on how to make a smart contract that uses the verifiable and distributed randomness from DIA called xRandom. If you haven't watched the introductory tutorial on what our randomness is and what are the use cases, what you can do there, I highly encourage you to click the link in the description where we have the introductory tutorial. So without further ado, let's start. I will show you a small smart contract example how to use this. Quick game of 2 players that want to play dice. The dice has 6 sides, so from 1 to 6, all the integers. And the players, they want to roll each one dice, and whoever has the higher number rolling should win the game. And if there is a draw, no one should win. So it's a totally fair game. Everyone has the same chance to win. If both players are not able to influence the dice, or in our example, the randomness that kind of constructs the dice. How do we achieve this? First of all, we have to import the function or the signature of the randomness oracle. Usually you can do this when you have the files open. I will just show you in the file system, and the files are directly next to each other. You just reference it like this, so that the compiler knows where to look for this file. And then you make your contract. We call it dice game in this example. You will always find this one in the documentation, so you can have a look there as well. What we are doing here is, first of all, we need to set the address of the random oracle, so that the deployed oracle is at some address. And here we configure it. So this is something we can do here. It's set in the constructor. So as soon as you deploy the dice game, you would have to input the oracle address, and then you can just take it from there. We also have variables called seed1 and seed2. These will be important for the players. I will show you in a second. And we have something called latest round ID, which, yes, as I showed you before, can be retrieved from the oracle, and where you should store what's the latest randomness round that the oracle knows, and what's the next one that you can actually use. We also have a function wrapper around the oracle so that we get a random value for a certain round. This is basically just returning. So we're calling the get random value for round from round for the round that we gave in, and this thing is called in context of the DIA random oracle contract. At the address random oracle. So this is basically just a function to have a bit of easier handling around getting a random value from this oracle by calling this function. Because by that then you can call this get random value directly in your contract. Now for the game, for the actual game, how should it work? So what we're doing here is we have player 1 and player 2, and they have each one distinct function, which is basically completely the same except for the name and for which seed it sets. So let's just check out what player 1 does to commit, and then player 2 basically does exactly the same. So player 1 needs to have one parameter, it's called seed, and this is something, for a dice game we could set it now between 1 and 6. So we have some checks that it's actually between 1 and 6. This seed is then stored in a variable. So basically seed1 is a variable that we have up here. So it's defined in the context of the smart contract. And basically, it's just so that we set the seed. And what we also do is we note what is the latest round ID. So we get the round ID from the randomness oracle by calling get last round. So this is what I showed you in the randomness contract. This can be done to show what has been the last round that the oracle actually used. Player 2 does the same. So here we see also they basically have a seed between 1 and 6. So it's bigger than 0 and smaller than 7. And it's an integer, so it's 1, 2, 3, 4, 5, or 6. And they commit the seed. This one is then called seed2. It's also up here. And they update the latest round ID. So whoever commits last updates the latest round ID, so that is clear. The latest round ID is something that has been, where both of them have committed this. Then the next one is actually the reveal phase. And reveal in this instance is called roll dice. So that means this is actually the execution of the protocol. So far we only have prepared the protocol, we only have prepared what players need to do. What we check here is that, yeah, the seed 1 exists, so that player 1 has committed. We can do this by checking if it's larger than 0, because if you remember, initially it was set to 0, but here it is set to something larger than 0. So if it's larger than 0, we know they have committed some seed. Same for player 2. And then, yeah, we basically do something where we say, okay, we take the round that we want to actually get from the smart contract to the latest committed round ID plus a safety buffer. So here it's 10, which means about 3 minutes. Could also be a larger or smaller safety buffer, but it should be at least more than 1. So that no one here can predict the last round already and basically, yeah, do the same without the commit reveal scheme. So there needs to be some safety buffer. So we recommend something like 10 to just wait a bit. So that also means that the roll dice can only be executed a few minutes after everyone has committed, because these 10 have to pass first. Because this is what we check here, that the last round is, yeah, larger or equal that committed round where everyone says, okay, we need to wait for the randomness to roll this dice. What we have then here is that we get the random value. So if the round is already passed, so let's say latest round plus 10 is 30 or something like that, and the actual current round is 32, then we can get the round, because this is true. Then we get the random value from actually round 30. So this is not the latest one, but this is specifically the one that was calculated here, regardless of what the current latest round is from the oracle. And then we just calculate the player results. So we do this by taking the randomness, encoding it with ABI encoding. That means that we get it into a format where we can hash it. This is a hash function, catchuck256. It's an inbuilt in the EVM, so it's very efficient to call. And we do this because the randomness itself is not necessarily uniformly distributed. The hash of it is always uniformly distributed. So we basically hash it, and then we convert it to a UN256 number, so it's an integer. Then we take the seed which was committed, because obviously these two are exactly the same for player 2 and player 1. And the seed is basically just, so yeah, this is kind of the personal input into the dice row. So we add the seed, so this is now a number plus seed 1 or number plus seed 2. And then we have a huge number, and what we then do is we take this number modulo 6, so that we get an actual dice throw result. That means that we have, we just take basically the last bits and check out what is modulo 6 for them. This is distributed randomly and distributed evenly enough so that it's a fair game. And what we can do then is that we check out player 1 result is bigger than player 2 result, then we return 1 for player 1 has won the game. Otherwise, if player 2 has a bigger number, then it's number 2 who has won the game, or else we return 0 for a draw. So now let's start by compiling and deploying the dice game to check out how it works. So first of all, we need to compile it. I have prepared this here. So what you can basically do here is just select the compiler version. Everything over 0.8.0 is okay, so 0.87 is absolutely fine. Then you click on compile. You can use this with any IDE or with any other development environment that you want. As you can see here, we have a few warnings but no errors, so this successfully compiled. Now we can deploy it. When deploying, make sure that you have the correct provider for your EVM. You can either use virtual machines that are coming with Remix. You can use environments like Hardhat, or like we do now, we will use MetaMask, because then we can just use MetaMask to deploy this on the network where we want to have it. As you can see here, we have a randomness demo wallet that I prepared. It's 0xBA8 something. And as you can see here, 0xBA8 something is exactly what we have. It's also showing the correct balance. And now we can use this to deploy. But we need to have, as you can see here in the constructor, we need to give in the address. So what I did is I opened the DR documentation and went to the Polygon Mumbai randomness oracle. You see here, there's some updates, and we get the address here. So we just copy the address, go back to our IDE, paste the address here, and then we click on deploy. What happens then is that MetaMask opens, and we can see, yeah, that we need to approve a transaction. MetaMask pops up with a new window, and we see that this is just like a normal MetaMask transaction. Then we click on confirm. Then you can see here in MetaMask the contract deployment will take some time. We can check it out in the block explorer. Yeah, it's pending, so it might take a few seconds or something until that is included in the block. As you can see now, the transaction has been included into the block and will be reflected in a short while. Let's do another refresh of the site and check out when the Explorer will have it. This will take, yeah, maybe a few seconds. I think it could be done by now or not. It's always a game of waiting a bit for the Explorer. I'm sure you all know this from your development. Especially on testnets, this can always take a time. What we can do in the meantime is we already see that there was a transaction recorded and we actually have a deployed contract which is shown here. So here we just have the contract to interact with. We could do now something roll dice. We could check out. This will probably fail because roll dice requires that both players committed their seeds, which they didn't. To prove that to you, I will just click on here. Then we are getting a warning. I will open the console down here and just making this a bit bigger. The console says the execution was reverted. Player 1 needs to commit their seed, which is exactly this error message here. Okay, then player 1 can commit their seed. So this is basically commit player 1, this function. Now I will be both players with my wallet, but obviously this can be done with any wallet. So player 1 is just committing a 4. They commit here. MetaMask opens again. MetaMask needs to be confirmed. I will show you here. So it needs to be approved. And we confirm this. Now you can see it's queued and it's pending. We can open again in the block explorer. And we see that it's ongoing here. We can, in the meantime, we can see the transaction from before is executed. It has been created, so we can check out the smart contract that we just deployed. So this is the game contract, where we can see this has been deployed and it's a new contract from 1 minute ago. What you also see here is that the commit player 1 is still on the way. So this transaction hash is now included in the block and will be reflected in a short while. In the meantime, what we can do, we can also commit for player 2 because this is obviously something that we need to do. Now we see here transaction has been mined, so this is now on the net. In the smart contract. Player 2 also commits something. They may be committing a 2. Note, this is not the dice they are rolling. This is just a number between 1 and 6, and this doesn't have an influence. So choosing a high or low number here obviously doesn't have a predictable influence in what you get. They just should be different so that they can roll different dice numbers, but the modulo here wraps around, so that means if we add, for example, 4 and if we add 2 here, that doesn't mean that the one with the 4 is automatically higher, because the number previously, which is this hashed number here, could be something that forces a wraparound when we watch it at modulo 6. So this is just to get different random numbers. So player 2 commits. Again, it's a transaction that needs to be executed, and as soon as we have that, we can check out MetaMask again. We see here, this is the deployment. This is the first player committing. This is now the second player committing. We can also check this out in the block explorer. By the way, this is the previous commit, so we see this has worked. We see here, it cost us a bit of gas, and we have some input data. If we decode it, we might be able to know. Okay, if we decode it, we see here there's some value in the front, and then a lot of zeros and then a 4. And this 4 is basically the dice value or the seed value that we just committed. and player 2 also has committed. So we see here the transaction has been mined. And we see here, this is a 2 they committed. So we can actually see in the smart contract explorer that this has worked and that we got the correct commits. What we can do now is we can try to roll the dice. This will probably not work yet because the 10 rounds have not passed, but let's see. So if you click this, exactly, you can see execution reverted, wait for the randomness round to roll your dice. So this means we now just need to wait a bit until enough rounds have passed. With 10 rounds, this means around 5 minutes. So yeah, see you back in 5 minutes. Yeah, we waited a few minutes, the 10 rounds should be over now, and we can call roll dice again to find out if it worked. And if we call it, we see here that we get the return value by our smart contract. The return value is 1, so we can see here. We can also see here that it's 1, so that means the player number 1 was the winner of the game, which is basically this case. So player 1 result was bigger than the result of player 2. This was totally unpredictable, so I couldn't predict who would win, obviously, because the randomness should guarantee that in any case. When designing such applications, you should be really aware that getting a commit reveal scheme going is very important, so that no one can predict what randomness is coming or even influence their own decision based on the to be expected randomness. One thing to also take home is this construction here. With the hashed ABI encoded random value that you then can cast into a UN256 integer, which will return you a uniformly distributed hash value which depends on the randomness. This makes it then possible to use it in some easy mathematical manipulations and to do a modular operation in it, which then for instance allows you to do the dice or to just get it from like 2 to the power of 256 numbers to a more usable range for your use case. You can also use this when you, for example, don't only put in the seed 1 or seed 2, but if you use it to generate a seed from other sources, like for example the block height or the last transaction ID. You can also use this to get multiple random values from one call to the randomness oracle. So this can be also helpful if you need to have a higher amount of transactions or of randomnesses in one transaction. Thank you so much for watching. This was a tutorial on how to get randomness from xRandom in a verifiable and distributed way on Polygon. If you want to learn more, please check out our documentation or the documentation of DRAND, especially if you want to learn a bit more about the cryptographic foundations, how to verify, and where the randomness is actually coming from. Stay also tuned for our next videos, where we will be showing you how to integrate xRandom in other L2 and L1 chains. But until then, happy hacking and have a great day.